how it is trained. Finally, we talked about some training algorithms like gradient descent, Newton's method, and least mean square method or stochastic gradient descent. So this adaptive, if we understand the adaptive filtering, then single layer perceptron is trained in a similar way as adaptive filter is trained. So basically, we can follow the same algorithm. So we feed patterns one by one to the single layer perceptron, and based on the desired response, we compute an error En. That error En is used to update the weights. So diagram of single layer perceptron is this. So so you have multiple inputs connected with weights W1, W2, Wn. These are summed up and passed through a. If we use this block Fi equals to Y, that means it is a regression problem. That is, output of the perceptron is directly passed. It is the final output. But if we deal with a classification problem, we map the output to either 1 or 0 or 1 minus 1, depending on our choice of threshold block. Okay, so here we can see one additional input, x0. We talked about m different inputs here, x1, x2. There are n different inputs, but one additional input we provide to the perceptron by setting it to 1, or it can be set to any constant value rather, but its weight is adaptable as all the other weights. So what is the use of this input? So basically, if we if we understand how adaptive filtering works, it basically fits a straight line. So like we finally get we combine all the inputs. X1 we multiply with W1, then X2 with W2, and so on. For all the inputs, if there are n inputs, Xn is combined with Wn. This is passed as the output of the adaptive filter. And the work of the filter is to find for which value of W1, W2, Wn we get the desired Y. So desired Y is known, given in the data set. Now we are trying to find out these parameters, W1, W2, these are called free parameters, which are adaptable. So for which set of parameters we are able to optimize the problem, or we get the actual desired value of Y. Achha. So now we can see this is a line that passes through origin. Like if x1, x2 all are set to 0, then Y equals to 0. So if we think of like one display, Y equals to some mx plus c in that form. So that is the equation of straight line, Y equals to mx plus c. So it draws some line like this. What is m? The slope of the line here, tan theta is m, or c is this intercept. Y intercept is called c. This we all know. But the line we are fitting using an adaptive linear filter has this form. That means if we just talk about single weight, it is of the form Y equals to x1 W1. If we have a single weight, this line always passes through origin. We do not have this C term here in this line, right? So that makes the fitting less flexible. For example, if we have a set of data points like this, if Y, X are deleted like this, some points are deleted like this, the actual, the correct line should look something, like this, which passes through the points. But using this model, the line that we will get is the best fit line that passes through origin. Some line we will get like this, because we don't have this bias term here. That's why this additional input is given to the neuron, which acts as a bias input. So it is always set to 1, and W0 is adaptable. So 1 into W0. So basically, along with Xi Wi, summation of Xi Wi, an additional term comes, that is W0. X0 is set to 1 usually. So X0 W0 is equal to W0. Since W0 is acts as the bias, so it gives the flexibility to fit this line also that does not pass through origin. So that's why when we use neural networks, we also add this input always to a neurons along with the other inputs. This is called the bias input. Okay. So now we get a straight line like this. And when we talk about a classification problem, so what we want is, so when we talk about a classification problem, our aim is to, okay, regression is fitting a line to a set of points that we just discussed. Our classification problem is, we have say two sets of classes, some class is here, some other class is here. And we want to fit a line that passes in between the two classes. Sorry, something changed. Okay, so these are the using this. So these are the two classes. We want to get a line that passes in between the two classes. So if we denote these two features as x1, x2, so finally, what neural network does is it takes x1, x2 along with the bias input. So this is x1, x2 along with the bias that is always set to 1. And here we have weight W0, W1, W2. And this summation is computed. So that is y. So summation of W0, x0 plus W1, x1 plus W2, x2. So this is computed. And now if this summation S, if S is greater than if S is greater than 0, then it will map to one class, say class 1, else class 0. Say two classes are there, else class 0. So that means for all the points on this side of the line, if we see the x1, x2 and W, if we get the value of S, that value will be greater than 0. So that will be mapped to class 1. All these points are mapped to class 1. And if it is less than 0, less than or equal to 0, that means even if the point is on the line, we will call it as class 0. So then we are mapping to this class, that is class -1. So basically equation of this line is W1 x1 plus W2 x2 equals to 0. So this is how we we can solve the same problem, but once we are if we use this as a linear function, we are thinking of a linear regression problem. If we use a function like this, step function, so this becomes a classification problem. Okay. So now, but one thing is for sure, that is single layer perceptron can only do classification of linearly separable classes. So if we have classes which are non-linearly separable, for example, if we have patterns like these are the, let's say, two features x1, x2. Patterns.
Sir, am I audible, sir?
Yes.
Sir, am I audible, sir? Sir, could
yes,
you please provide? Could you please provide us the notes, sir, from which you are displaying everything, the topic, sir? Is it possible to share the notes, sir?
Note means PPT.
Yes, sir. Yes, sir.
Yesterday I emailed. Did you not receive that?
No, sir. No. Till today, we have not received any PPT, sir.
But yesterday I sent an email. 1 minute.
Yes, sir.
Anyone received my PPT yesterday?
Yes, sir. I have received.
My mouse is...
I haven't received any PPT, sir, since the starting day.
Starting day I cannot say, but yesterday I sent this mail.
Yes, sir. Where I will find this, sir? Please convey, sir.
You got this email from office?
No, I haven't received this, sir, from office. Yes, and I have not received, sir.
This email you did not receive yesterday from PLC office. So
I haven't received, sir.
okay. So
Please resend, sir.
So how will I share with you separately? I have sent to this group mail, but I need
Okay,
to.
I'm rechecking, sir. Please pardon me. I'm rechecking, sir.
You can check once, sir.
Yes, sir. Thank you, sir.
Acha. Okay, so now coming to how it is, how to fit, like coming to regression problem in more depth. So let us say we have a set of points. These points are shown here, and my question is, which is the best fit for this set of points? So all the four graphs have the same set of points, and in the first line, in the first figure, we have plot this this curve, sine curve like thing. Acha. Okay, no, in the second plot, okay, so this visually this looks to be a very good fit visually. So this is basically the ideal fit, this line. I am just putting my mouse over it. This line seems to be the ideal fit for this set of points, right?
Sir, I have received, sir. Thank you, sir.
Thank you for it.
I have received.
Okay.
Today also, please share. Yes, sir. Thank you, sir.
I am talking about the same PPT, but when I will start genetic algorithm, I will share that. Okay. So if we fit a 0-degree polynomial to this set of points, so m equals to 0 means 0-degree polynomial. So it is basically some line parallel to x-axis. So this is the simplest fit or best fit. So this line basically we can move up or down, but it is always parallel to x-axis. So it is the simplest fit, but we can understand it is not a very good fit, or it does not fit the set of points very accurately. If we are able to add some slope to this line, for example, consider the second figure, we can adjust the inclination of the line, slope of the line, and we get somewhat better fit with 1-degree polynomial, somewhat better fit, but it still is not a very good fit. Like if we consider the ideal fit, it's still far from that. Visually we are saying. So this third one, okay, it is more close to the ideal fit. Let's say this is a 3-degree polynomial, so maximum degree is 3. And the final one is the best fit in the sense that it passes through all the points. If you look into the curve, so it is passing through all the points, right? Whereas in the third case, it is passing, not exactly through all the points, but it is following the trend of the data. So if we make the model more and more complex, or if we increase the, in this case, value of m, say degree, polynomial degree, then we are gradually going towards better and better fit. But if model is very simple, my fit will not be always very accurate. As you can see, m equals to 1. So this is the case of single layer perceptron. It fits a straight line, but it cannot fit nonlinear data very well. So based on this, based on whatever discussions we had, we must have some method of fitting nonlinear lines. So the line we are fitting should not be straight line like this, rather it should be curved. But how much curved, that is a question that we do not know, because always we cannot see the data points in space. They are very high dimensional data, and it's very difficult to visualize them always. So we go for, by default, we go for multi-layer perceptron, instead of single layer perceptron, to fit nonlinear lines or to classify nonlinearly separable patterns. So the architecture of multi-layer perceptron is like this. So this it has input layer, as you can see. This is there in single layer perceptron also, where we put the inputs to the network or to the neuron. Okay, so after the input layer, we have a set of hidden layers. So there can be multiple hidden layers, 1, 2, 3, 4. In this diagram, we have shown 2 hidden layers. Okay, so in MLP, we can have even 10, 15 as we want. Then we have the final. After all the hidden layers, we have the final output layer. Okay, so output layer where we are getting the output from the neural network. So in simplest case, we have one hidden layer, one input layer, one output layer. If we have more than, lot of layers, more than one layer, that means 2 or 3 or 4. So gradually we go from shallow learning to deep learning. So if we have a single hidden layer, we call that as a shallow learning network. And if we have 2, 3, 4 or 10 layers, we call them as deep learning networks. Okay, so that is the difference. But the learning technique, the way the network learns, that is same for shallow or deep. What happens is, if we go for more and more layers, we are able to fit more complicated lines to the model. Okay, but if we go for shallow networks, then the line becomes less complicated. Acha. So now if we carefully look into the diagram, to the architecture of the neural network. So if you see the first hidden layer, it gets input from all the inputs in the input layer, from all the nodes in the input layer. So there is an arrow from first input, from second, from third, and from the last. So all the inputs come to this neuron. Similarly, for the next neuron, all the inputs in the input layer are passed to this to each neuron in the first hidden layer. Then when we talk of second hidden layer, then all the outputs from each neuron of this first hidden layer, so first output, then from second neuron, second output, third neuron, third output, and so on. So all these outputs come to each neuron in the second hidden layer. So this is called a fully connected network. We call this type of networks as fully connected networks, because all the inputs or all the outputs from the previous layer, all the outputs come to each neuron in the current layer. Okay, and so we for each of these neurons we add a bias signal also, that we have already discussed. So why bias is added, we have already discussed. So finally we have the output layer. It receives the output from the previous hidden layer, from all the neurons in the previous hidden layer. Okay, so now how many neurons we will have in each layer, that is the next question. So when we talk about says any classification problem, so that means we have got a training data set where we have labeled patterns. So we got some set of patterns and the corresponding class that is given in the training data set. Now we are training a model with that data set. So we know how many classes are present in that data set, how many categories are present. So accordingly, we will fix the number of output neurons. Say if we have a problem that does dog versus cat classification, so we will use a we will use a neural network that has 2 output neurons, 2 neurons in the output layer. If we deal with a problem that has 3 classes, then we will take 3 neurons in the output layer. Okay, and input layer, again the number of inputs is fixed. So it is basically the dimension of the feature vector that we are providing, that is given in the dataset. So all the features must have same dimension. So that is one limitation of multi-layer or any perceptron model. That feature, it cannot have different dimensional features. So all the features must be of same dimension. Achha. So now coming to the hidden layers, we can have 1 or more hidden layers, and number of neurons in each hidden layer can be varied. That is user input. We can have 4 hidden neurons or 5 or 6. So that depends on the programmer, the one who is programming the model. Okay, but input and output layer must be fixed for a given problem. So the things, the parameters, so one we talked about free parameters. So weights, biases, these are called free parameters. Why? Because while training the network, we adjust these weights and biases. But this number of neurons or number of layers, hidden layers, these parameters cannot be dynamically adapted. So we call these parameters as hyperparameters of the network. Okay, so hyperparameters are set by the user before starting to train the model. Free parameters are those parameters that are adjusted while training the model. For example, these weights, the weight magnitudes we can adjust while training the model. In hyperparameter, we can consider this number of hidden layers, number of neurons in each hidden layer, the learning rate of the model. So all these are called hyperparameters. Okay, so choosing the right set of hyperparameter is also very much important when we think of training a neural network. So another very important point is actually these neurons. We are seeing that okay, it receives inputs from the previous layer. So now this neuron takes all the weighted summation of the inputs, and like single layer perceptron, we have seen it passes through a threshold block to do the classification. In this case, we use some activation function like that, like not the threshold activation function, but some activation function which is differentiable. So it is a nonlinear activation function which is differentiable. Because if we cannot use this type of function, it is a non-differentiable function, as we can see clearly. At this point it is non-differentiable, at this point also it is not differentiable. So we need a differentiable function. Why we need that we will understand if we understand how the weights are updated. So network contains one or more layers that are hidden. These are the hidden layers, and there is a high degree of connectivity. And how to decide number of output layer neurons, that I just told you. So if we deal with the 4 class classification problems, a pedestrian, car, motorcycle and truck are the 4 classes. So we will have 4 output neurons in for the multi-layer perceptron. So each output neuron corresponds to 1 class. So if we feed this pedestrian image at the input, say if we are able to represent each of this image as a 3-dimensional vector, so that is passed to the input, 3-dimensional input, then all the computations happen in the hidden layers. There can be more than 5 neurons in each hidden layer, and finally we get some value at each output neuron. The ideal value, the desired value will be 1 0 0 0 for pedestrian. That means we want this neuron to fire when the input is pedestrian. If the input is a car, we want the second neuron to fire. So desired output will be 0 1 0 0. So if the input is a motorcycle, the output neuron, this third output neuron should fire. So 0 0 1 0 is the desired output. Now neural network will not give exactly 1 here and 0. So it will give some fractional numbers here. So the error we can compute at each neuron. So if it gives say 0.8 at the first neuron, 0.3 at the second neuron, 0.2 at the third neuron. So the error at the first neuron is 1 minus 0.8. The error at the second neuron is 0 minus 0.3 and so on. So based on this error, we can do the back propagation. That means we can adjust the previous weights based on the error that we make at each output neuron. Okay, so these weight updates are also done layer by layer. So first, weights from output to the previous hidden layer, all these weights get updated. Then the weights from this hidden layer to the previous hidden layer, all these set of weights get updated. Then finally from this hidden layer to the input layer, all the weights get updated. So first is, given an image, we form a vector out of that. So that is the input. Then we forward propagate that signal in this direction. We get some value at the output neuron. That means we are making some error at the output neuron. So based on that error value, we back propagate the signals to the input layer. Any questions till now? Any questions? Okay, so let us see how how we train a neural network. So I will use my this whiteboard to explain. So if you do not understand at any point, please stop me. Otherwise, I will continue. So as we can see, the architecture of multi-layer perceptron. So we have set of inputs. Okay, so this is the input layer basically. Then we have the hidden layer. So hidden layer, let's say we have some neurons. Inputs can be, this layer can be just external signals, or this can be output of some other neural network also. Basically we are getting some values x1, x2, etc. here up to say xm. Say let's say m dimensional input. So m inputs, and along with that we add a bias always. Then coming to hidden layer, we have say this is first hidden neuron, second hidden neuron, up to say nth hidden neuron. So this is hidden layer with n neurons. Then we have the output layer, and I am just considering one hidden layer now, but the discussion can be extended to multiple hidden layers. So let's say we have p neurons at the output layer. Okay, so at okay, so now how this connect? How are the connections? So each input in input layer are connected to each neuron in the hidden layer. So there is a connection like this. All the inputs are connected to each neuron. Similarly, x0 is connected with this neuron, x1, x2. All these connections are there, and similarly this connection. Here also we have these connections. I have drawn this like dot dot dot, means there are other neurons, they are connected in a similar way. Okay, so on top of hidden layer also we have a bias which is coming to each neuron in the output layer. So it is connected like this. So this completes the diagram. If we define the symbol, so xi means ith input. Okay, now if I denote w, say ih, h, this is h, is the weight from ith input to hth hidden neuron. So that means let's consider this is the second hidden neuron, this is the first hidden neuron. So w, this weight connecting x0 to neuron 2 will be written as w02 in as per this notation. The weight connecting second neuron to nth hidden neuron will be w2n. Okay, so now if I compute the weighted summation at the say jth hidden neuron, or let's say we are writing hidden neuron as h, so I am using the same notation h. So hth hidden neuron, the weighted summation at the hth hidden neuron we are writing as yh equals to summation of xi wi h. So this I varies from 0 to m. So for all the inputs, x0 multiplied by, say, consider this second hidden neuron, x0 multiplied by w02 plus x1 multiplied by w12, x2 multiplied by w22. So this summation is computed basically. Now we said that this neuron computes the weighted summation and passes it through some nonlinear but differentiable activation function. So the output from the neuron after passing through the nonlinear differentiable activation function is VH, denoted by VH. So this is output of hidden neuron. Okay, so VH is basically if you pass YH through some nonlinear differentiable activation function. So we are writing that function as phi. Next, this from here we get, from the first hidden neuron we get V1 as output, from second hidden neuron we get V2 as output. So H varies from 1 to up to n. There are n such hidden neurons and output layer as P neurons. So each of these n neurons come to each neuron in the output layer. So if we compute the weighted summation at each output neuron, let's say we denote that as ZK, output neuron. So ZK equals to VH multiplied by WHK. Is it clear? Like K is the kth output neuron and H is the hth hidden neuron. So the output from the hth hidden neuron is VH, that is multiplied by WHK, and that is summation over all H equals to 0 to n. So basically V0 we don't have, we have first hidden neuron, second. This V0 is the bias which is always set to 1. So here we have V0, which is the external bias signal that is coming. We set that to 1 into WHK. And now this at the output neuron also we pass it through another activation function, and finally we get the output from each output neuron. So this is again, let's say, the same activation function we can use, or they can be different. I'm writing phi 1, phi 2 basically. So there are P output neurons. So for each of these P output neurons, we get this value at the output layer. Okay, and now we also know the desired response at each output layer. So if we call that as decay, that is the desired response, desired output at kth output neuron. We are getting okay, but actually we should have got decay. So we are making some error at each output neuron. This error is decay desired minus predicted. Okay is predicted, decay is the desired. So we can compute E1, E2, and so for all these P output neurons, here we are computing error E1, here we are computing error E2, here we are computing error EP. Now these errors, now we will apply stochastic gradient descent. So errors are used to update the weights of the network. So the whatever we have written till now, this is called the forward propagation phase. So signals are passed forward in the forward direction. Now after we compute the errors, we go for back propagation. That means we pass this error signal in the backward direction until we reach the input layer. So first, how we have seen the weight update expression when we learned stochastic gradient descent minus eta del C del W. This is the weight update expression, and for stochastic gradient descent we said that we do not know the exact shape of the cost function. We only have a set of input-output patterns. So we we find the instantaneous value of the cost function and whatever error we make for that. So the instantaneous cost function is defined as C equals to half of summation E square, EK square. So for when we feed one pattern, we are getting E1, E2, EP output. So if we square them and sum them up at the output neuron, and half is the additional factor. If we just multiply this with half, then we are getting an estimate of the cost function at the output layer for a given input. So from here, if we compute DC dW, whatever weight we want to adjust, that is W. So if we want to adjust this weight connecting second hidden neuron to the first output neuron, that will be W21 in this case. So del C, del W21 we have to find. In general, any weight from hidden to output neuron we are writing as WH0, WHK. So we will find, so to update weight from hidden to output layer. So any weight we are denoting them as WHK. H is hidden to Kth output. So this is true for all the weights depending on the values of H and K. So basically delta W HK. So currently we have initialized this with some value, some random value. And with those random values we have made all these computations. Now the change in that value will be denoted by WHK equals to minus of eta del C del WHK. As per stochastic gradient descent rule. So we just have to compute this expression, multiply with minus eta, we will get our weight update expression. So here we apply the chain rule of differentiation. Minus eta is there. What is del C del WHK? So we don't find any direct relation between C and WHK, but we can apply chain rule. So C is related with EK, so del C del EK we can write. Then EK is related with OK, so del EK del OK. Then OK is related with ZK, so del OK del ZK. ZK is related with WHK, so del ZK del WHK. So this is my weight update expression. Now we can easily compute them. So it will be minus eta del C del E is EK simply. Then del EK del OK is minus 1. Here we are just having minus. Then del OK del ZK is we have one activation function phi 2. That's why we said it should be differentiable. So we can see that we have to differentiate the activation function. If we use a non-differentiable activation function, we cannot compute this differentiation. So depending on the function, we can compute the derivative. I am writing as phi dash derivative at ZK. Then del ZK del WHK is VH simply. So this is the weight update expression. So this minus becomes plus. Basically eta into EK phi 2 dash ZK into VH. So if we are computing this term, we will add this to the previous weight. So that will be my new weights, new set of weights we will get. So in this way we can vary H and K, we will get the update expressions for all these weights connecting hidden to output layer. Next, if we want to update weight from input to hidden layer. So this is slightly, not difficult, but we cannot do it just directly through chain rule of differentiation. So this is denoted as WIH. IH. So we have to compute this term del C del WIH. Then we will multiply with minus eta, we will get the weight update expression. So del C del WIH, if we can see that, again we will go backwards, but one important point is that, so let's go backward. Del EK is related to OK, OK is related to ZK, ZK is related to VH, del VH is related to del YH, del YH is related to del WIH. But But one point we have to note that, so if we want to update say this weight, the effect of all the output neurons comes into play. So if we write del OK, EK, these are specific to kth output neuron, but effect of all the output neurons comes into play when we update this weight. So basically when we have this K term involved, we sum over all the K's here up to this term. So K equals to 1 to P. If we make this summation, and then we multiply with VH, del YH, del W. So we will get the final weight update expression. So this again we can solve very easily. K equals to 1 to P, del C del EK is EK, del EK del OK is -1, del OK del ZK is phi 2 dash ZK. This is WHK. Now multiplied with del YH, VH is derivative of this activation function. Del YH, WH is Xi. So this is the weight update expression from hidden to input to hidden layer. So important point to note here is that this derivative of activation functions get multiplied. So what happens is, the functions we usually consider, the activation functions we usually consider here are sigmoid or tan hyperbolic, etc. So these activation functions, for sigmoid activation function, if we consider, let's say sigmoid activation function is defined in this way: 1 by 1 plus e to the power minus x. So whatever is the input, we compute e to the power minus of that 1 by 1 plus. The shape of the curve is this. At minus infinity, if we put minus infinity, it is 0. So when x is minus infinity, it is 0. When x is 0, the value of phi is 0.5. And when x is more than 0, it is now at infinity, its value is +1. This is 0, this is 0.5. So this is the shape of the sigmoid curve. And if we compute, here we need, while forward propagation, we need to compute this phi. But while backward propagation, we need to compute phi dash. It can be shown that phi dash of this function is phi into 1. We can prove this easily. If we just find the derivative, and we can show that phi dash is equal to phi into 1 minus phi. So when we can show this thing, we can again show one more thing here. That is the range of the gradient of sigmoid function. Gradient of this function, the minimum value is 0. When phi is 0, the value is 0 definitely. So at minus infinity value is 0, at plus infinity also phi is 0. So phi dash is 0. That means the gradient is parallel to x-axis, but the maximum gradient is at phi equals to, the maximum gradient that we achieve here is at this point. So it is at, the maximum gradient is 0.25. When x is plus infinity and x is minus infinity, the gradient is 0. But when x is 0, the gradient is 0.25. So this is the maximum gradient that is achieved by sigmoid function. Minimum is 0, maximum is 0.25. If we use another activation function which is tan hyperbolic, its minimum is 0, maximum is 1. We can show that. Okay, so what happens is if we use sigmoid function in all the layers, and if the network is very deep, so there are a lot of layers, then what happens, layer wise these phi values get multiplied. So maximum value that phi can achieve is 0.25 if we use sigmoid function, and these get multiplied. If we have more layers, these get multiplied more number of times. So ultimately it leads to a very small number, the multiplication of gradients. So finally what happens, the effective change in weight, this del C del WH becomes very close to 0, like this number. if we have lot of layers and we use sigmoid activation function, so which problem we call as vanishing gradient problem. So neuron stops learning. If the weight update is 0, that means neuron is not learning anything. So to avoid that, nowadays we have some other activation functions which we call as ReLU or leaky ReLU, which are better in that aspect. Like it does not lead to vanishing gradient. At the final output layer, we can use sigmoid, but before the output layer, in the other layers, if we use ReLU or leaky ReLU, it is a it avoids this, or it can effectively tackle this vanishing gradient issue. Achha, any questions till now? Any questions? No. So let's discuss one more important concept related to classification.
Sir, am I audible, sir?
Yes.
So what is stochastic, like you said, stochastic regression, or like what you said, I could not understand.
Stochastic gradient.
Yes, sir. Stochastic, and yes, sir.
Stochastic
Please elaborate something.
That we discussed in yesterday's session. The SDL gradient descent algorithm. So it's there in my slide. So basically, what we are doing here, this C equals to, we are writing this term, half EK square, the weighted, the summation of squared errors. So this is basically an estimate of the cost function. We are saying when we feed one pattern, we are getting some error at the output neuron. So cost function, if we see how C varies with, if we write C as a function of this weight vector. So how C varies with respect to W, that we do not know. It can be some curve like this. But at this value of W, for a certain choice of W, we have initialized these weights randomly. For a certain choice of W, we are estimating the value of C as half of EK squared. So we are initializing the weight randomly. Let's say here we have this weight, and for that we are estimating this value of C. We do not know the shape of C, but we are estimating the value of the cost function at this point, and what can be the gradient at that point. So that gradient we are computing here. So that's why it is called stochastic gradient descent. It is not the exact gradient descent, but we are estimating.
Thank you.
Okay. Another important discussion related to classification, we have, how good we can train a classification model. So to discuss that, let us consider this figure. So we have plotted weight and height of a set of mice in this graph, and we want to see the how height is related with weight, how height of mice is related with weight. So clearly, from visually we can see the relationship is not linear, rather there is a non-linear dependency of height with respect to weight. So this is the ideal relation that we can visualize. The graph is like this. Why we need to fit this relationship curve is that given any weight of the mice, we can predict what will be the height of the mice. So that is again a regression problem. Now question of fitting is there. Visually we have fit this line, but when we use neural network, we want the neural network to estimate this line basically. Now how complicated we will make the neural network? If we use single layer perceptron, it will fit a straight line. If we fit multi-layer perceptron, it can fit non-linear line, but the degree of non-linearity matters also. So if we use a multi-layer perceptron with more number of layers, it can learn more non-linearity. Okay, so let's divide the entire data set into training and test set. So these blue dots represent the training set and green dots represent the test set. So now if we fit the data, fit a line, let's say we use a single layer perceptron, we fit this straight line. This straight line is shown here. Okay, so straight line does not capture the true relationship between height and weight. Okay, that is so we already understood, and the inability of machine learning algorithm to capture this true relationship, this is called a bias of the machine learning model. So this term is very important. This is not the same bias we discussed for neural network. So this is the training error basically. So training, we have a training data and the machine learning model cannot capture the true relationship of the training set, which is called a bias. One measure of bias can be the error that we make for the training data. So if we see the prediction, okay, my model is drawing this straight line, means it is saying, okay, for this weight, this should be the height. Actually the height is this. So this is the error that my model is making for this weight. If I take this weight, my model prediction is this, but actual height of the animal is this. So this error we are making. So if we are able to find these distances of each point from the line and we can square them and sum them up, then we can say this is a measure of the bias, the training error. Total error we are making in training. Okay, so if we are able to...
Sir, am I audible, sir? Sir.
Yes.
So, in practical real life, how we can be sure that what kind of model we have to prepare on the basis of a data set, sir?
We cannot be sure in any case, but through experiments we can come up with a good model. So yes, for that we need to consider a validation set, and there are certain theories that yes, if I get time I will try to discuss after discussing this bias variance thing. So how to decide on the model hyperparameter
model? Yes sir, yes sir. What kind of models are best suited for like this purpose? Yes sir. Thank you sir. Thank you.
Okay, so only thing is, if we are able to, we had fit this straight line, but if we are able to fit this curved line, then we could capture the true relationship between weight and height. So if we are able to fit this line, my training error will be 0. But we have fit this line, so we have got some training error. But the problem comes. This is a very important problem in machine learning that I am talking about. The problem comes when we consider the test data. So if you consider the training data only, so this line, as per our understanding, this line is a bad fit, this is a very good fit because it passes through all the points. But if we consider the test set, we had some green dots also, no? So now we can see the fitted line, how much error it is making on the test set. So for the straight line, it is making roughly the same error as it made on the training set. But for the test set, the error is huge now. Whereas, in this case, if we fit the curved line, it was perfectly fitting the training data, but it is making a large error on the test data. So errors, are these distances. So now, in terms of fitting the test data properly, straight line wins over this curved line. So one thing we can see here, if we make the model very complex, if we constrain the model to pass through all the points, then what happens is the model learns the training data very well. Its training error is almost 0, but its performance on unknown data suffers. Whereas a relatively simpler model performs consistently good or bad on all the data sets. So the question that was asked to me is very much related to this, like how to choose a model now. Which model shall we choose? So we should not go for over complicated models and we should not go for very simplistic models. We have to stay somewhere in between the two. Okay, so this property or this property of a machine learning model, that it has high variability in prediction. So you, for some data sets it is giving very accurate prediction, and for some data sets, like for in this case it is giving very accurate prediction, but if the data set changes, its prediction is suffering a lot. So there is a lot of variance in the prediction. We call this term as variance. So this bias versus variance trade-off is a very important concept in machine learning. So if we want to reduce the bias, so bias means the error we are making on the training data. So if we want to reduce the bias, then we have to go for more and more complicated models. That means it will fit the training data more and more accurately. But doing so, we are losing the generalization property of the model. That means the variability of the model suffers. So its prediction on unknown data becomes more and more unpredictable. It can make either very good prediction or very bad prediction. So this is called bias versus variance trade-off. This can be explained. This is a very popular diagram which is used to explain bias variance. So basically it shows that, I mean, you want to hit the target, so you are always able to hit it within this red zone. So your prediction is not varying much, so its variability is low and your bias is also low. You are always able to hit the target. The second diagram shows your bias is relatively low. So that means you are always close to the target. You are in the second zone, but you have high variance in the throws. Like sometimes you are throwing this side, and so on. But bias is bit, almost close to the target. In this diagram we have low variance but high bias. That means we are hitting the second zone. We are a bit far away from the target, but variance is less. You are almost hitting the same zone always. And the last case is high bias, high variance. This is the worst possible case. We do not want this type of models where the bias is very high, variance is also very high. Ideally, we want this thing where we have low bias and low variance, but always that is not possible to achieve. So we have to choose like something. We have to choose the trade-off between bias and variance properly. Okay. So what happens, like if we have low bias, we are fitting a straight line. Consider this classification problem. We have some cross. This is one class, and circles represent another class. So very simple models, single layer perceptron fits a straight line. And a very complex model, if you have multi-layer perceptron with lot of layers, it will fit this line. So which classifies the training data very accurately. Like all the stars, all the crosses are on one side of the line, all the circles are on other side of the line. So this model is not good because we can clearly see that this circle is a noisy point. Like visually we can see it falls in between all the crosses. But if we make a very complex model, it learns noise as well. So it will draw the line in this way. So this model has better generalization. So it is fitting a smoother line, not a very complicated line, but it has some training error, but its prediction will be more or less accurate on the test data. Whereas in this case, the training error is 0. The bias is 0, but variance will be high. This particular case is also called overfitting. So when we are learning the noise, our prediction on training dataset is very good, but our prediction on unknown dataset is very bad. Overfitting case. Underfitting is when we are unable to capture the true relationship in the dataset. And this is classified with medium level of complexity. Okay, so I just wanted to discuss all these things on artificial neural network, but since one question was asked, like how we choose the best model. So as such, there is no such hard proven rule that this will always give you the best model. Rather, we follow one strategy normally. So what we do is we have this training data. This is the training data based on which we want to train our model. And we do not take all the data for training, rather we divide it into two parts. So one part we call as validation data, another part we call as training data. Training and validation set basically. Test set is different, which we cannot use at all during the training process. So the entire data set is training data is divided into training and validation data. So what happens is training data means we have some patterns are there along with the labels. So for validation data also we have patterns along with the labels. And there are different ways of dividing these different validation techniques. We have k-fold validation, we have leave one out validation. Many different techniques are there. But to keep it very simple, let us say we divide this entire data set, like training data set, into three parts. Okay. So this we are talking about threefold cross validation. CV I am writing cross validation. And these three parts, what happens? At a time, we train the model. We are taking any model, either single layer or multi-layer perceptron. It has a lot of weights. So we train the model on two parts. So part 1 and 2 and 3. Three parts we have divided. We train the model on part 1 and 2. Part 1 and 2 and we test on part 3. So we get an idea of how the model is performing when the data set is unknown. So 3 is not used for training the model. We are just using 3 for testing, but we know the levels, so we can observe the model's prediction and we can compute accuracy or loss, whatever. Next, what we can do, if we train the model with part 1 and part 2, we test on part 3, we can get a test accuracy. We can call test accuracy on part 3. Similarly, we can train the model on part 1 and 3. We can get a test accuracy part 2. We can train the model on parts 2 and 3. We can get a test accuracy for the part 1. So these 3 test accuracies we got, we can average them. So this gives a estimate of how the model will perform on unknown data. So now, how to fit the best model? There are no well-proven algorithms for that. What we normally do, so we have set of hyperparameters, say multi-layer perceptron, we have learning rate, number of neurons in the hidden layer, say number of hidden layers also. So 3 hyperparameters, we call them as hyperparameters, which constants we have to set initially. Okay, so we basically choose we fix different configurations. Let's say 50 different configurations. Like for of eta NL, say eta is 0.2, number of hidden neurons is 5, number of layers is 1. This is configuration 1. Second case, eta is 0.05, number of hidden neurons is 10, number of layers is 2. So likewise, let's say we consider different configurations, and for each of these configurations we can compute the average cross-validation accuracy. The configuration that gives the best cross-validation accuracy can be considered as your preferred model for a particular data set. And now that model can be used to work on the test data, which is unknown. So basically what you are doing is from the training data set, you are just picking up part of the data to observe how your model will perform in unknown situations, that is test situations. You get an estimate of that performance. So this is one of the techniques we call them, this technique is, technically this is called grid search with cross validation. So grid search means we are searching this grid, and with cross validation we are searching, which the configuration that gives the best cross validation accuracy is the what desired model. Any other questions on artificial neural network? Whatever we have covered is quite less, but there are many more things to cover in artificial neural network. We have gone through two basic models. Like if you want to practice problems or coding, so there is a repository which we use normally, UCI machine learning repository. Here you will get a list of data sets. You just search in Google with UCI machine learning repository. There are several data sets, and we can take one of these data sets and implement a particular machine learning model and study that ourselves. So that is a good starting point. Regarding coding language, any coding language can be used, but in MATLAB you get some in MATLAB, Python, like more advanced coding languages, so some libraries are there which already gives you the functions to train multi-layer perceptron. Basically you just have to call that function. You do not need to write any lines of code. You just call the function, it will do the training for you. But if we want to code in C, then we have to write the entire coding by hand. And normally I recommend my students to write in C because it gives us a better understanding level. Exactly how the model is working, we can understand better if we code in C. Any questions on this topic, artificial neural network?
Sir, am I audible?
Yes.
Sir, you have very nicely stated the gradient part and mathematical portion, especially of this artificial neural network. Sir, can you suggest any book which covers the mathematical analysis of ANN and all?
Take. You can refer to this book, Neural Networks, a Comprehensive Foundation, by author name is Simon Hekin. So I am basically following this book only.
Okay, sir.
You will get all the mathematics there.
Sir, is it freely available?
The ebook is available online, freely available.
Thank you, sir. Thank you very much.
Okay. So we will start genetic algorithms after this. So if you have some questions, I can try to answer. Otherwise, I can just start with genetic algorithm. Okay, so so now this is a very different topic. In artificial intelligence, it is whatever we are discussing are all parts of artificial intelligence. So this is called basically when we learn genetic algorithm, we will not find any mathematical logic. We should not look for any mathematical logic here. Like in neural networks, we are able to get some logic why we are doing certain operation. Genetic algorithm is purely the operators that we will see, they are motivated from biology, like this theory of natural evolution. From there, it is motivated. So if we think of this story, like how we are here in the world today. Initially, dinosaurs used to roam here. Very big animals used to roam on Earth. So then gradually they became extinct, and we are, constantly evolving. And now we are the most intelligent animals on Earth. Okay, so after this, probably again, we will get more improved animals, more improved creatures will dominate. So basically what happens, in the context of what we will study in genetic algorithm, if I speak, so initially there is a population. That population means there is a lot of animals are there. Some of them are good, some of them are bad. Good in the sense, let's say, intelligent. Some of them are more intelligent, some of them are less intelligent. Some of them are more powerful, some of them are less powerful. So if we think of a single objective, let's say intelligence is my criteria, then based on only intelligence, we can say, okay, some of the initial population were more intelligent than the others. One of them is best. Then we have lot of people, lot of animals. Some of them have less level of intelligence, some of them have more. Now what happens? From here, a selected set of individuals undergo certain reproduction operations, and new offspring are generated. So it's natural evolution, as I said. The new offsprings have a tendency to keep the traits of their parents, and sometimes they even improve upon their parents. But as a whole, the population becomes better and better. Why? Because, say, dinosaurs were less intelligent. They probably ate a lot of food, more than they need. That's why food became scarce and they gradually became extinct. Humans are good at more intelligent, are good at preserving their food and eat. So they are more intelligent in how to effectively eat the food. So our food never becomes extinct, and we can generate foods also. So my point is, I am trying to talk about survival of the fittest. So this is a very common term in Darwinian theory, that the fittest individuals will have a chance to survive more. And in the coming population also, like even say million years from now, humans will have more tendency to survive than some other animals which are less intelligent than humans. So this is survival of the fittest. So genetic algorithm is inspired by all these processes, natural processes. But here, as population, we consider a set of solutions of a problem. Set of solutions, among them which solution is best, that we want to figure out. So this is also an optimization technique. Like we can consider any function, let's say fx equals to 5x squared plus 7x plus 3, maximize this function. So this is an optimization problem. So genetic algorithm can be used to solve this type of functions. Okay, so it is an optimization technique, but the way we solve this a problem using genetic algorithm is very different from how we solve other problems in mathematics. So I will, since it is a very big topic, I mean, in my slide, I have tried to cover the important points. At least the algorithm I want to make clear to you. And I will also talk about certain like problems and how genetic algorithm can be applied to solve such problems. Okay, so it is a type of evolutionary algorithm. As I said, it follows natural theory of evolution, suitable to solve problems that are computationally hard and involve large number of parameters. So this is a very theoretical term, computationally hard. So for example, let's say, I mean, we can easily solve sorry, so let's say if so x square equals to 9 and I am telling you x is greater than 0. So we know the answer. There is a like well-known mathematical theory that tells us how to find x from x square equals to 9. Even if I give you like say x square minus 5x plus 3 equals to 0, solve for x. So that there also we have some Sridhar Acharya formula. So some mathematical logic exists for that. But if I give a very different problem, say 7 to the power x plus 5 divided by x plus log x minus 5 equals to 5 to the power x. Just a random equation I am writing involving x. To solve this, we do not know any straightforward mathematical steps or any algorithm that can solve this problem. So one option is, if we know the range of x, suppose someone tells us x varies within a certain range, we can try to put some numbers in that range and check whether this expression, the value of this expression is close to 5 to the power x or not. But that becomes a very computationally hard. That is the point, that it involves large number of, lot of calculations, basically. So which is difficult to do for all of us. So in these cases, we go for this evolutionary algorithm, search strategies. One of them is genetic algorithm. This was first introduced by Professor Holland. For genetic algorithm, you can refer to his book also. It is a very well-known book on genetic algorithm. In 1965. So it follows basically two fundamental biological processes. One is genetics, that means the reproduction, etc., those operations, and second is evolution, how population changes in different generations. So there are different, I am coming directly to the algorithm, so I am not discussing anything about biology, coming directly to the actual problem. So there are three different ways of solving a problem using genetic algorithm. We will discuss the simple genetic algorithm. So there are steady state. Basically, operators are same, just the way you apply the operators, that becomes different in steady state and messy. So this is the basic framework of how we apply genetic algorithm. It can look very complicated if you are very unfamiliar with the topics, but I will try to explain each thing step by step. So this is a flow chart. This diagram is called a flow chart. Arrows represent the flow of information. So you can see initially start, after that create a population. So whenever we are discussing something, try to find analogy with the theory of evolution. So there is an initial population of size n. Now evaluate, second we have this block, evaluate each individual based on some objective. So if we consider intelligence as objective, so similarly, in genetic algorithm we have something called fitness of a population. How fit is a population? How fit is an individual in a population? The more the individual is fit, the more is its chance to survive in the next generation. Okay, so evaluate means basically we assign a number to each member of the population, each individual in the population. The higher the number, the better is the individual. So that means it has more chance of surviving in the next generation. So after evaluating, then we decide some convergence, basically how many generations to how many generations we will go through, or some criteria is there, like that we will discuss later. So if convergence criteria is not met, so after evaluating each individual, we create a pool which is called the mating pool. This selection, so from this population we select NP, so P percentage of the actual number of members in the population, we write that as NP, individuals. So mating pool means here in this mating pool reproduction will take place. So our objective is to get the better members from the population in the mating pool, so that we get good quality offsprings also in the mating pool. We try not to take very bad members from the initial population in the mating pool. So very bad, very good, how we are deciding? Based on the number that this evaluation step has assigned. Very good population will have a higher number, bad populations will have a lower number associated with them. So next, in the mating pool, what we do is we select pairs of solutions, pairs of individuals, and perform certain reproduction operations. So one of them is called crossover, then mutation, inversion is another thing. So some reproduction happens inside mating pool, so the solutions or the individuals get changed. That means from parents we get offsprings. So gradually, individuals are changed. Next, these mating pool solutions, we replace that in the original population. So this arrow is there. We replace the original. So initially we had a population, we selected some of them based on the fitness. Then we perform certain reproduction steps, and then after reproduction we put that individuals back to the original population. Okay, so this goes on in a loop. As you can see, this thing goes on in a loop. And so how long will it continue? Definitely we have to set the number of iterations. So that is convergence criteria. If it crosses some number of iterations, we stop. Another way is, if this fitness, we are computing fitness here of each individual, if it does not change, the average fitness of the population remains almost constant, we stop the algorithm. So once we stop the algorithm, we get a set of individuals like in this population. So among them, the best individual is returned as the desired solution. So let's go step by step. So initial population, we are considering n size is n. Mating pool, we are taking p percentage NP. That's a convergence threshold, something. Or these things we will talk about. The inversion is different, mutation and crossover we will talk in this session. What are mutation probability, crossover probability, that also we will discuss. Okay, so now let us come directly to how we do genetic algorithm. Consider any such optimization function. Let's say we want to optimize this thing. Say some function x square minus 5x plus 3. We want to find the minimum value of this function, say in the range minus 50 to plus 70. This problem is given to us. Minimize this thing in this range, or some range is given. So basically it is a very simple problem. In real life we should not apply genetic algorithm to solve this, but just for explanation I am taking a very simple problem. So first step is, if you remember the diagram, initial population, create initial population of size n. So there are different encoding schemes. One of them is called binary encoding. We also have real number encoding. So what we basically do, a solution is represented as a binary string like this, 0 or 1. Binary string means 0 or 1. So we decide the length of the string, say 10 or 20, whatever, that is something we decide. Fill those 20 bits with 0 or 1 randomly. So one set of 20 bits represents one solution, another set of 20 bits represent another solution. So likewise we generate n different solutions, create a population of size n. So basically, I mean, we just say, if we decide we will use 4-bit encoding, 4-bit binary encoding. So maximum number is 2 to the power 4. So many bit strings we can generate, 0000, 0001, 0010, and so on. So what we will try to do, we will not generate all these 16. Basically we do not encode in 4 bits, we use much larger number of bits, but we do not go through all the possible bit strings. That will be a brute force search. Genetic algorithm is intelligent. It is called heuristic search. So we will randomly generate strings of 0 or 1. So let's say first string is 00, 10, 10, 0100, and instead of 16, let us generate only 5. 1001, 0111. So some can be repeated also. And if we take, say, here 20 bits, so there can be 2 to the power 20 different possibilities. We can generate only 100 strings out of 2 to the power 20. So that is how it is intelligent. So it does not consider all the possible combinations of zeros and ones. It considers a few number. From there it will try to alter the solutions through reproduction and try to search for even better solutions. Okay, so this is how we represent a individual in a population. In genetic algorithm term, we call them as chromosomes. So each individual is called a chromosome. So here what we have drawn is, this is one chromosome, this first one is one chromosome, C1, this is second chromosome, this is third, this is fourth. So if we generate 100 such strings, there will be 100 chromosomes. Okay. For example, let's say this is the function given to us, so this can be one possible encoding for X. So first step is encoding. So if we decide first how many bits we will use for encoding, and then we randomly generate 0 or 1 for those number of bits. So once this is done, I am not talking about real number encoding. Today we will only talk about binary encoding. So if we have multiple variables involving X and Y, so basically this will be X, Y, not only X. So if we have multiple variables, then we in the chromosome we have two parts. One part will be for X, another part will be for Y. And for each part we generate 5-bit strings. As per your choice, you can generate 10-bit or 20-bit strings also. Real value I am skipping today. I'm not discussing this real value encoding. It's same. Basically, instead of binary number, we are generating real numbers here. Acha. If we think of a different type of problem, whatever we discussed is binary encoding. Say for a problem like where we need to arrange some things. I think all of you know about traveling salesman problem. I have it in my slide later. So the problem is we have a set of cities as given in the diagram. All the dots represent the cities. So we have a starting city. From there we visit all other cities and then we come back to the starting city. So this is the problem, says that we have to visit all the cities only once. Like each city cannot be visited 2 times, but our total distance traveled has to be minimized. So if we have a map of all the cities, that is, if we know the latitude and longitude of the cities, then what will be the order of visiting? So here we are not trying to find out any value of x that optimizes some function. Rather, we want to find the optimal ordering. City 1, then after city 1 shall we visit city 5 or city 10, like that. So for that we use order encoding. So order encoding is basically, it can be a permutation of all the cities. Achha. So one example of that is this traveling salesman, as I said. So we are given a cost of visiting one city from another city. Basically, we know this matrix. So cost can be the distance between 2 cities. Let's say if we consider this figure, we have 5 cities and the distance between each pair of cities is given as numbers here. If 2 cities are not directly connected, that is given as infinity. Okay, so now suppose starting city is A. You want to, the problem is visit C, B, D and D, come back to A, visit all other cities exactly once and come back to A, but your total distance traveled has to be minimized. So from A, one option is from A you can go to B, from B you can go to C, C to D, but that does not cover all the cities. E is missed. So from A you can go to E, then B, then C, D, again come back to A. So this is one of the options. So this matrix is given basically, that in which what is the distance between each pair of cities, and from that we have to estimate what will be the shortest possible tour. Okay, so this is how we define the cost. Okay, so if we come up with some ordering of the cities, let's say here we have 5 cities, so one particular, so C1, C2, C3, C4, C5, 5 cities are there, A, B, C, D basically. So order encoding states you consider, so how many possible combinations can be there? You are starting from city 1, visiting these 4 cities in any order, so 4 factorial combination, basically it's 24 different combination. So if the number of cities increases, 24 is still, we can search manually, we can compute the total distance traveled for 24 times, we can do that and find out the minimum. So it is possible. But if the number of cities increases to 100, then we have to compute 99 factorial, which is a very large number. And this brute force search method will take a lot of time. So genetic algorithm becomes handy there. So we write the cities in some ordering. That is one chromosome here. Let's say after C1 I am visiting C4, then C2, then C5, then C3. So let's say this is one of the ordering. So what is the what is the total distance traveled here? So C1 to C4, so A to D distance is 6, plus C4 to C2, D to B, D to B distance is infinity, and so plus whatever, it is very high, distance is very high. So likewise, we can consider another ordering of the cities. Let's say from C1 you go to C3 first, then C5, then C2, then C4, then come back to C1. So we will get some number here which represents the distance that I will travel if I follow this ordering. So we generate a set of chromosomes. So if there is 5 cities, there are 4 factorial possible combinations. Out of them, let's say we consider 10 different configurations, and for each of these 10 we can find the total distance traveled. Now among them, one will be very good, that means for some chromosome the distance will be very less, for some the distance will be quite high, right? So that number, that cost, total distance travel, we can write in this form. From I equals to 0 to n minus 2 distance ci to ci plus 1, and then finally the last city to the 0th city. This summation we are basically computing here. So our task is to minimize the cost. So this cost can be considered as a metric of how fit a chromosome is. So as I said previously, if a chromosome is more fit, we will give it a higher fitness value. So, but in this particular problem, the lower the cost, the better is the solution. So the lower the distance traveled, the better is the solution. So 1 by the distance traveled, 1 by D can be, or we can add a small quantity, because if D is 0, then it becomes undefined. Some epsilon we can add. So this can be considered as a fitness function to decide how good a chromosome is. So we will find this summation 1 by D will give an estimate of how fit this chromosome is, how fit this chromosome is. The higher the value, the better is the solution. So that is the idea. Another example is 01 knapsack problem. So how it is defined? So there are n items, and n items, each item, for each item we have some cost and some weight, and we have a bag of capacity W. Okay, so what I want to take all these items in my bag. So my total weight should not exceed W. So each item has some weight associated, but I want to maximize the cost of the items that I am taking. So this diagram will help us understand. Let's say I have my first item has weight 10 kg or whatever, that is not mentioned here. Let's say kg, 10 kg, and its cost is $60. Second item has weight 20, its cost is $100. Third item has cost 30, its cost is $120. I have a bag of capacity 50, which cannot hold all the 3 items. It can hold I2, I3, or I1, I2, or I1, I3. It cannot hold all the 3 together because its capacity is 50. But my objective is I will fill the knapsack with maximum profit. So I will take as many items as possible, but while taking the items, I have to also take care of the profit that I am making. So if I take, say, I2 and I3, then my total cost is 100 plus 120, 220. If I take I1 and I2, then I cannot take I3 because it's exceeding the capacity. I1, I2, I am making $160, which is less than the taking I2, I3. If I take I1 and I3, I am making $180. Still it is, weight is 40, so it is less than 50. I cannot take I2 anymore. So this is the problem. The brute force approach will be to take all possible combinations, like you take only first item or only second item or only third item, or any combination of two items or all the three items. So you can search manually which of these yields more profit. There are how many possible cases? 2 to the power n minus 1 possibilities. Now if we consider encoding this thing, we can one of the encoding scheme can be, if you take an item or you take a 3-bit string which denotes whether you have taken an item or you have not taken an item. If you have taken an item, you make the first, if you take the first item, you make the first bit 1. If you take the second item, you make the second bit 1. If you take the third item, you make the third bit 1. If you do not take an item, you make that bit 0. So there are, like if we consider 3-bit strings, there are 2 to the power 3 cases. So first case is 0, 0, 0, that is you have not taken any item. Then 0, 0, 1 means you have taken the third item. 0, 1, 0 means you have taken the second item. 1, 1, 1 means you have taken all the items. 1, 1, 0 means you have taken first and second item. So if this is a very simple case, ideally we will have lot of items, and so we cannot do with 3 bits. So if there are 100 items, we have to consider 100 bits. And manually searching like 2 to the power 100 possibilities is tedious. So we have to go for intelligent search techniques. Okay, so this is, I'm just trying to discuss how encoding is done. So for order encoding, we have seen one case, the previous case, traveling salesman problem. Ordering of the cities can be considered as an encoding. Here, here order is not important. I1 and you take I1 first, then I2, or you take I2 first, then I1. That is immaterial. So here it follows this type of encoding scheme. If you take an item, it is 1. If you do not take an item, it is 0. So now we have generated a population. So given the problem, we decide the encoding scheme. Now we have generated a population. So next we take some of these and put into the mating pool to do reproduction. So for this, we perform some selection step. So from this original population, we select some of them and we put into the mating pool. So okay, I have probably missed some slides, but I am discussing. I will put it later. Basically, I have lot of slides. I tried to pick up the important ones. Selection slide I am searching for. Anyway, I can explain on whiteboard if I am missing those slides right now. So what happens? So once I decide on the encoding scheme, next step is from the population I select some of them. So this is the initial population. I select some of them and I put them inside a mating pool. Mating pool is again a smaller population. This is the larger population which has say n individuals. Here we take p% of n. and always my objective is to select the better individuals from the population, so that my offsprings are better. There are different selection techniques. So one of them is called canonical selection. I mean the simplest one, canonical selection. So what we do, we have this population, let's say X. I am drawing a population of 5 individuals, X4, X5. Say I have done some binary encoding 0010 of 4 bits. Okay, so let's say I want to minimize this function x square minus 5. So so what I can do is, I assign some fitness values to each of these. That means fitness values means which indicates how close this number, how much it minimizes this. Say x square minus 5. If I do simple binary encoding, so 0010 basically means decimal 2. 1011 basically means decimal 11. 1100 is 12. 0110 is 6, and this is 8. So the decimal number corresponding to each binary string. This is simple binary encoding. So x square minus 5, so this will give me 2 square minus 5, 11 square minus 5, 12 square minus 5, 6 square minus 5, 8 square minus 5. So this is basically minus 1, this is 121 minus 5 is 116, this is 144 minus 5 is 139, this is 36 minus 5 is 31, 64 minus 5 is 59. Okay, so for each of these chromosomes I can get a number which indicates how close or how I am able to minimize, which one minimizes this function more. Okay, so now we can see this is the best answer for all among all these. After this, probably this is the second best, this is the third best. If I rank them, this is the best, this is second, third, this is fourth, this is fifth. So among all the solution, this is 2 is my best solution. So if I am able to rank them, that okay, this is my best solution 1, this is 2, this is 3, this is 4, this is 5. If I can rank them, and depending on my mating pool size, my mating pool, let's say for 5 chromosome it is of size 3. So I will take the best 3 solution, that is I will take x1, x4, x5, so into this mating pool. So 0, 0, 1, 0, 0, 1, 1, 0. This, out of these 5 individuals, these 3 will come into mating pool. So canonical selection basically what it does, it ranks the individuals based on some fitness, and then it selects the individuals based on the ranking. Okay, so this has both advantage and disadvantage. The advantage is that we are losing the bad solutions. So this 12 is a very bad solution, I am losing it. Okay, I am just keeping these 3. But another difficulty with canonical selection is, if suppose the function I am optimizing has this shape, and the population I have generated, so this is the optimum value, the minimum value of this function. So if this is fx, this is x. So if I am generating these values randomly, initial 0 and 1. So suppose I have not got any solution around this region. I have got all solutions generated. I mean all these values of x I have generated, but nothing near the actual optimum solution. What can happen is, if I take the best 3 here, I will get some solution near the local optima, not the actual global optima. I will, okay, I have generated solutions in this range. In this range, this is the optima. So I will get all solutions near this. I will not reach the global optima. That is one of the limitations of canonical selection. Okay, so a better version of this is Rowlett-Will selection. Rowlett-Will selection, a slightly better version of canonical selection, that we are going to discuss next, but I think we can take a short break, then come back again. Okay, so let's have a small break. So we will again meet around 5:15. Okay. Acha, you have some question? Any of you have some question?
Sure, sir.
Okay. Okay, so welcome back. We will continue our discussion on genetic algorithm.
Yes, sir.
So basically, we were talking about selection algorithms. So first one is canonical selection, and next another selection algorithm we call it as, Rowlett wheel selection. There are different selection schemes. These are some important ones we are discussing. So in Rowlett wheel, what we do, we basically find the fitness values of each member of the population. So, for example, I do not see the eraser here. So, for example, let's say I have some chromosome X1, X2, again, let's say 5 chromosomes, X3, X4, X5. I find some fitness value. Let's say the fitness value is for this chromosome is 20, for this it is 10, it is 5, it is 100, it is say 80. So fitness values, how to get these values? Fitness indicates how fit a chromosome is. So higher the value, higher is the fitness. So this is the meaning of fitness. So with respect to our previous problem where we were minimizing some functions x square minus 5, we had considered several values for x1, x2, x3, x4, x5. These are randomly generated binary strings. From them we can find the decimal value of x, and x square minus 5 we can compute. So x1 was probably giving -1 and then some other value. So we said this is the best in our last discussion. So, but in this case, the value that is least, say this is 8, this is 100, this is 0, this is say 5. So among these things, this is the best chromosome with respect to minimization problem. If we compute x square minus 5. So, no, this is not best because we have 0. Let's say this is 10. So the closer it is to the -1 is slightly better than 0. That is okay. So so this is the best solution. Second best is this. Second best is x5. So if we rank them, x1 is best, then x5, then x2, then x4, then x3. Yes, but the numbers are not in increasing order. Like the best one should have highest fitness value. So in this particular case, x4 is best, which has the highest value. In this particular case, x1 is best, which has the minimum value. So one option is we can just use some function which converts this minimization problem to a maximization problem. So that type of function can be used to find the fitness function. We can call them as the fitness function. So if we are able to get these fitness values for each chromosome, next what we can do, we can think of we are discussing about Rowlett wheel. So some concept of wheel should come. So we can think of a wheel here which can be divided into 5 sectors. The area of each sector is proportional to the fitness value. So basically for each sector, say x1, this is 20, the fitness value is 20. And if you compute the summation of all the fitness values, this is 20 plus 10, 35, 135 plus 80. So 215. So let's say 215 into 360 degrees. So this is the angle
The slide is not yet shared.
Oh, sorry. Okay. Okay, so yeah, so we were discussing about this particular case. We have 5 chromosomes, and these are the fitness values associated with each chromosome. Higher the fitness value, the more fit is the chromosome. Okay, so now we think of a Rowlett wheel where we divide this wheel into the number of sectors equal to number of chromosomes. We have 5 chromosomes here, so we divide this wheel into 5 sectors. The area of each sector is proportional to the fitness value. So how to get the fitness area for chromosome X1? We can just find 20 divided by the total fitness summation of all the fitness values into 360. This is the degree. So let's say, in this particular case, X3 will have smallest area, X2 next, X1 next, X5, X4 will have the largest area. So if I start here, let's say this is X1, then this area is assigned for X2, this area is assigned for X3, and X4 will have maximum area, and then X5. So this is X1, X2, X3, X4, X5, and these angles we can get by computing this expression. Like for each angle, if we divide by total sum of all the fitness values multiplied by 360, we get the corresponding angles. So now in canonical selection, what we did, we always selected the best 3 chromosomes. If my mating pool has size 3, we selected the best 3 chromosomes into the mating pool. In Rowlett wheel, and that has a disadvantage that we discussed, that we can also converge at the local optima. We may not get the global optima. So sometimes, at least in the initial phases of the genetic algorithm, when all the populations are random, so it is good to get some bad solutions also in the mating pool. Why? Because if we get all solutions cluttered around the local optima, then even after the next reproduction operators that we will learn, we will never come close to a global optimum solution. We will always stay around the local optima. Say this is the global optima. Curve looks like this. 1 minute. So if the curve looks like this, so this is the global optima, and then we have local optima. So our solutions are in this range. We have not got any solution here. So if we get a very bad solution, say this is a bad solution because it has very high value, our objective is to minimize. So if we are able to select this solution also in the mating pool, then along with these good solutions, locally good solutions, we also have a bad solution. So when we will do crossover next, the next reproduction operators, we have the chance of fusing this solution and one of these solution to get something in this range, some solution in this range. We will generate a new solution in this range. So we will have some chance of going towards the global optimum solution. So Rowlett wheel gives us that chance. Here also we have more probability of selecting the better solutions, but we also have very less probability of selecting the bad solutions. That is, chromosome with fitness 5 can also get selected, but with a very less probability. How this algorithm works is like this. So we divide the circle into some sectors. Each sector corresponds to one particular chromosome. So now we rotate this circle in any direction, clockwise or anti-clockwise. Okay, and we have a head here. So after rotating this wheel, so rotation is done about this point. Here it is fixed to the wall, let's say, and we are rotating the wheel, and this wheel will rotate, and at some point it will stop. So the sector at which this arrow will point, we will pick up that chromosome. So if after rotating once it points to X2, we will pick chromosome X2 in the mating pool. Again we will rotate the wheel. So if we get X4, we will put X4 in the mating pool. Again we will rotate the wheel. If we get x4, we will put x4 here. Again we will rotate. If we get x5, we will write x5 here. So how many times we will rotate the wheel? That is equal to the size of the mating pool. So size of the mating pool, number of chromosomes we want to select. So this also gives us an outside chance to select x3, because after rotating x3 can also come in front of the head, but that chance is very less. Okay, so canonical selection eliminates that chance completely, but here we have a small chance of selecting very bad chromosomes also. And so we how to implement this in when we do programming. So basically, I mean, you can find the normalized fitness values. So for x1, normalized fitness value is 20 divided by summation of all the fitness values, that is 215. For x2, it is 10 by 215 and so on. And then you compute the cumulative fitness values. So here it will be 20 by 2 by 5. This is 20 plus 10, so 30 by 215 and so on. So cumulative fitness values we can compute. So finally we get some values in the range 0 to 1. So next you generate some random number in this range. If it is say 0.5, the random number generated is 0.5. Okay, then the chromosome corresponding to which the cumulative frequency value first process 0.5, that will be selected. Right, so let's say so this is 20 by 2 by 5, this is 30 by 2 by 5, so this is still less than 0.5. When we add x1, so it will be again plus 5, so say x3, so we will get 35 by 215. Cumulative, I think all of you know how to calculate, so it is just summing over the previous value. So in this way, if we continue, when we have x4, we will cross the 0.5. So if we just find these numbers, then when we have x4, it will be 35 plus 100. So 135 by 215, which is more than 0.5. So we will select x4. If when we rotate the, I mean, the way we are implementing this operation is equivalent to saying that we are rotating the wheel, wheel is stopping at some point. So this random number generated in the range 0 to 1, this comes from uniform distribution. So any number can be generated. So it can be 0.2, 0.3, but numbers in this range where x4 lies will have more chance of getting generated because this area is larger. So here also we will have more chance, like for different random numbers, we have more chance of selecting x4 compared to x1, x2, x3, etc. But we also have some chance of selecting x1, x3. Okay, so this is called Rowlett wheel selection. What happens is it does not eliminate the chance of bad individuals to come to the mating pool. It selects good individuals, but it also keeps, I mean, it can keep bad solution in the mating pool. So with this, we come to a very important term called selection pressure, which is a very important term in genetic algorithm. How much constant we are applying on the selection algorithm, that you have to select the best individuals. So if we compare different selection algorithms in terms of selection pressure, canonical has highest selection pressure because it is ranking the chromosomes first and selecting only the best ones. So its selection pressure is highest. Then comes Rowlett wheel. So it's less than canonical, but it's also high. Like we are still encouraging good solutions to come to the mating pool. Okay. So there are other different selection schemes. Like there is a modification of Rowlett wheel. We call it as rank based selection. Basically, what happens, like as I said, Rowlett based selection. Here we assign areas in Rowlett wheel selection, areas are proportional to fitness values. So chromosome fitness and the area allocated inside the circle, these are proportional. So what happens if we have some, one very good chromosome, okay, in the population, so let's say its fitness is 100, and there are other 4 members' fitnesses are very low, 2, 5, 1, 3, etc. So when we apply Rowlett wheel selection here, so in most cases, all the solutions that will come in the mating pool is this first solution, because the area allocated in the circle for this one will be the highest. Let's say this much area is allocated, and for other chromosomes fall in this range. Very small areas are allocated. Most of the times, the head that I was talking about will come to this sector after rotating the wheel. So the mating pool will get same copies of the same chromosome all the time. So X1 will come always after Rowlett wheel selection. To avoid this, we go for rank-based selection. So here what we do, instead of taking the raw fitness values, we rank the fitnesses. So this is in reverse order. So the chromosome which has lowest fitness, the chromosome fitness 1 is given rank 1. Chromosome with fitness 2 is given rank 2. Chromosome with fitness 3 is given rank 3. Chromosome with fitness 5 is given rank 4. This is rank 5. So now this area allocation is done based on these ranks. So it will allow less disparity. So previously we had, this much area for one chromosome and very small area for other chromosomes. Now if area is proportional to the ranks, we are still able to give more area to this chromosome which has highest fitness, but we also have some areas for each of the other chromosomes. So rank-based selection is used if there is wide disparity in the fitness values. So Rowlett will give you same copies of same chromosome in mating pool, which rank-based selection tries to avoid. So next, after selection, so these slides I will find in my laptop somewhere. It must be there. So I will put it in this our TLC slides. Okay. So after this thing, we have the next step. Next step is we are in the mating pool now. So what happens in this mating pool? So we have an original population which is very large. From there we have applied selection. We have taken a small set of individuals. Out of 1,000, we have taken 100 in the mating pool. So now among these 100 solutions, we will combine 2 solutions and we will try to generate new solutions. To make it simple, let us say our mating pool has 6 solutions instead of 100. So solution 1, solution 2, 3, 4, 5, 6. Okay, so now we will, in the mating pool, the first operator is crossover operator. So what we do, we select pairs of solution. We decide, okay, this and this solution will be combined with each other. So if I name them 1, 2, 3, 4, 5, 6. So I am saying 1 and 2 will get combined. So this we randomly decide which 2 solutions will get combined. Let's say 3 and 4 will get combined and 5 and 6 will get combined. But 1 can be also combined with 3, 1 with 6 also. So it is randomly decided. So 3, 4 gets combined, 5, 6 gets combined. After combination, we get 2 new solutions, say 1 dash, 2 dash, 3 dash, 4 dash, 5 dash, 6 dash. So these are, like, we call them as offspring. So these are parent chromosomes and these are offspring chromosomes, or children of the parent chromosomes basically. So from 2 parents we get 2 children. So this is crossover. So how it is done? that we are going to discuss. There are different ways to do crossover. Among them, we will discuss a few. So, single point crossover. How it is done? So, we have these two parents. Let's say this is one solution. This is one more solution. Two parents are combined to get two offsprings. So, first we decide a crossover point. So in this particular case, these are 8-bit strings, as you can see. So crossover point can be any number between 1 and L. So if we can either do crossover after first bit or after second bit or third bit or fourth bit or fifth, sixth, seventh. So we can do crossover at any one point. So this is called a single point crossover. What it means basically, about that point we exchange the bits. So if you see, if we decide this second point is my crossover point, that is after second bit we will do the crossover. And these two parent chromosomes we can see. So the offspring will look like this. So the first 2 bits will come from parent 1 for offspring 1. The next 6 bits will come from parent 2. For offspring 2, the first 2 bits will come from parent 2. The next 6 bits will come from parent 1. So basically, the genetic content of two parents are combined to get new offsprings. This is called single point crossover. We are dealing with, we are doing exchange about 1 point only. This particular technique has some limitations. One of them is called positional bias. Okay, so we are not going into so much technical details today because it is just a 2-hour session. But to remove those limitations, to come across those limitations, some extended version of single point crossover have also been developed. That is, one of them is called multi-point crossover. So instead of exchanging genetic content about 1 point, there we consider multiple points. For example, in this particular case, we have 3 points, K1, K2, K3. The offsprings will be like exchanged about these points. So you can understand from the diagram, this for offspring 1, this small part from parent 1 comes, then this part from parent 2, this part from parent 1, and this small part from parent 2. Similarly, for offspring 2, the reverse thing happens. This technique reduces the positional bias to a certain extent. Positional bias, I can explain in a very simple way. For example, in single point crossover, whatever crossover point we choose, so crossover points can be chosen after first bit, after second bit, or so on. Whatever we choose, the first bit will never change. Parent 1 and offspring 1 will always have the same bit. Parent 2 and offspring 2, the starting bit will always be same. So this is one of the positional bias that is present in these crossover schemes. And likewise, we have other types of crossover. One of them is called uniform crossover. So what we do, basically, we have two parents. So this basically gets rid of all the biases. So at each bit position, we toss a coin or we choose a random number between 0 and 1. So both numbers are equiprobable. So toss and coin means head and tail both are equiprobable. And we define a rule. If the outcome of the toss is head, then we will swap the bits between parent 1 and parent 2. If the outcome of the toss is tail, we will not swap the bits. So that rule we can define, and so accordingly we can generate new offsprings. So as I said at the beginning, we will not look for any mathematical proof behind that. These are set of algorithms defined which we follow, and it has been seen to work well in most of the cases, genetic algorithm. So let's say the rule is if the toss is 0, then swap the bits between P1 and P2. So when we toss the coin for the first bit, outcome is 1. So we will not swap the bits. So offspring 1 and offspring 2 has same bit as parent 1, parent 2. If it is 0, then we swap the bits. So 1 gets swapped with 1. Effectively, there is no effect of swapping. Both are 1. So in this case, output is 0. So bits get swapped. 1 comes in offspring 1, 0 comes in offspring 2. So at each bit position, we toss a coin and we swap the bits. If the outcome of the toss is 0. Okay, so here, as we can see, there are some redundant swappings also. Like if both bits are same, then there is no point tossing the coin at that bit, because outcome is 1 means we will not swap, outcome 0 means we will swap. So if both the bits are same, swapping and not swapping does not make any difference. To improve that, there is another technique called half uniform crossover, where we just swap for non-matching bits, or we toss the coin for non-matching bits. So if the wherever bits are matching in the two parents, 1 are matching, so we are not tossing the coin at this point. These two are not matching, so we toss the coin here. Outcome is 1. So here we have defined the rule as if toss is 1, then swap the bits, else remain as it is. So here output is 1, so bits are swapped. Output is 0, bits are not swapped. Output is 1, bits are swapped. So we are reducing the number of tossing basically by checking this condition. If both the bits are same, we are not tossing at that point. Okay. Similarly, there are other different crossover techniques. I'm not going to all of them. So crossover basic idea is to combine two parents and generate two offsprings. Okay. So like single point crossover has some problems, some biases that we introduce. One of them is positional bias, endpoint bias. This is an important problem. Like if we have when we do crossover, what we said, we are always following natural theory of evolution. So our expectation is that children will carry some traits from their parents. In terms of genetic algorithm, what it means basically, if the parents are solutions in a certain range, like say if I just draw the same diagram again, x fx. So if this is the function, if we choose one parent here, x1, another parent here, x2, then and combine these two using single point crossover or whatever, multi-point crossover, the new solutions that will be generated will be close to x1, x2. That means they will retain some properties of x1 and x2. They will have something in common. The children will have some properties common as their parents. It will not be, the new solutions will not be very far from the parents. That is the idea. Hamming-Cliff problem is like if you have two chromosomes like this, like if you have a chromosome 1000, 1000, so first bit is 1, second bit is 0, third bit is 0, fourth bit is 0, and you cross over with another parent, you get this as one of the children, 0, 1, 1, 1. That means 111 is coming from another parent. So 1 bit change can make a, but effectively, if you just consider the binary binary to decimal. So 1000 means 8, 0111 means 7. So in decimal, as such, there is very less difference between the two numbers. But if we consider the number of non-matching bits, this is very high. It is 4. All the bits are not matching. So, but in decimal, there is just, one difference in the two numbers. Similarly here, the reverse thing, the 0000 to 1000. So 0000 means decimal 0 and 1000 means decimal 8. Here only one bit is not matching, the first bit. Hamming distance is one number of non-matching bits. But the distance, like decimal distance, if you consider, that is 8. So one bit change can make a very large or small jump. That is the problem with crossover techniques. Okay, for binary encoded chromosomes. So this we can handle in some case when we go for real encoded chromosomes. Okay. Achha. So then the next reproduction operator, is called mutation. Mutation, as we have heard a lot during COVID times, that some virus is getting mutated very frequently. And it is getting new variants which is difficult to again attack. So it's difficult to find the right medicine to tackle the new mutated virus. So mutation basically means abrupt change in genetic content. So what happens? Mutation is a genetic operator to maintain genetic diversity from one generation to next. So what we do in binary coded GS, we flip the bit from 0 to 1 or from 1 to 0. But we do that with a very less probability, which we call as mutation probability. So initially I have shown you a slide where I have written crossover probability and mutation probability. So crossover normally happens with a higher probability because we want new solutions to get generated from parent solutions. And mutation means it is drastically changing the genetic content. So we want that with a less probability. For example, if we are supposed towards the final phases of genetic algorithm, we are converging towards the optimal solution. So most of the solutions get scattered, get clustered around this optimal point. At this point, if we give a very high mutation probability, what will happen is the solutions will get again diversified. So this solution can come here, some solution can come here. So it will again become very random. Why mutation is useful? It abruptly changes the genetic content that I said. So again, if you think in this way, like if say most of my solutions get clustered around some local optima. This is the global optima, and my solutions get clustered here. This normally genetic algorithm tends to cluster solutions around each optima. Okay, and after multiple iterations of genetic algorithm, I have not got any solution here. All the solutions are getting clustered here. Another way we can think, x1, x2, we have lot of solutions, 100. Say all the starting bits have become 0, 0, 0, 1, 0, 0, 1, 0, 1, so 0. And there are other bits also. So 0, 0, 0, 1, 1, so whatever. So starting bits are 0 always. And if you convert into decimal, they all lie in some range, in the lower range. Starting bits are all 0. And using crossover or other genetic operators, we can do any crossover, half uniform, single point, multi-point. The first bit will not change, it will remain as 0. Effectively, what we are doing, we are combining solutions in this region to generate some other solution in this region only. We will get new solution, but it will be in this range only, starting bit 0. So mutation helps in this aspect. If the population gets converged around the local optima, it can abruptly change the first bit to 1. So one solution can randomly suddenly come here with mutation. That is useful because we can combine one solution from this region and one solution from this region to get something in between, some solution here. Again, this can be combined with some solution here to get the actual optimal solution here, global optimal solution. So mutation drastically changes the genetic content, but it happens with a very less probability. If we do mutation at all the bits with a very high probability, then all the solutions will become very random. So it will happen only to 1 or 2 solution, and that too at only 1 or 2 bit positions. All the bit positions will not be affected. So that's why mutation probability is kept very small. So mutation probability we write as mu_m is kept very small, and crossover probability is kept relatively large because we want new solutions to be generated. Okay, so basic genetic algorithm is this. So if we consider some specific problems, let us consider. So let's say, how to decide in which type of problem we will use genetic algorithm. That is first question. Second is, if we apply genetic algorithm, what to encode as a chromosome? We are always talking about generate a population of solutions. So what is my solution? That is the question. So genetic algorithm can be applied for some only optimization problem where we have a single objective. That is the first point. So single objective optimization problems. Single objective. Okay. If we have multiple objectives, genetic algorithm cannot be applied like in its simplest form. Say you go to buy a car in a shop, so your objective is to minimize cost or maximize comfort. Both are like inversely related. If you go for minimizing cost, your comfort will also ideally reduce, but you want to balance the two. This type of problems cannot be solved using genetic algorithm. If your objective is only to minimize cost, you can solve using genetic algorithm. If your objective is only maximize comfort, you can solve using genetic algorithm. But for multi-objective optimization, we cannot use genetic algorithm to solve that. Okay, so however, there are bypass techniques like maximum. If we are able to write a function, say FC represents the function to compute cost. So we are trying to minimize cost. Or say fx, depending on some parameters x, or some car is x, f of x gives the cost of x, or g of x gives the comfort of x. So some functions are there. So this is a maximization function, this is a minimization function. So this maximization can be converted to a minimization function, say fx plus 1 by gx or something like that. So this we can try to minimize as a whole using genetic algorithm. So it is, if we have multiple objectives, we will try to combine them as a single objective. Otherwise, genetic algorithm can be applied to only single objective problems. So one of the example, let us consider the same linear regression problem that we have done using single layer perceptron. So in single layer perceptron, we had a neuron here. We tried to feed the inputs, then pass through a identity mapping function, then we get the output. Here weighted summation is taken. Based on the output, we add up the weights, and finally we come up with the new weights. When we solve the same problem using genetic algorithm, so first question we have to ask is, what is the final output, or in linear regression, what we want to get finally? We want to get a straight line. That is the answer. So question is, what we want to get out of the algorithm is a straight line. Answer is a straight line. So in genetic algorithm, how well will we get a straight line? We get some solutions. So basically how to define a straight line? Y equals to mx plus c. So if we know m and c, we can know any straight line. Okay. So in genetic algorithm, we will take m and c as the two factors to write a chromosome. So basically the chromosome first part will be M, the second part will be C. So we will have binary encoding for both M and C, so depending on number of bits. So likewise we will generate lot of such solutions initially. Then we will apply some selection algorithm. So we will generate lot of solution, let's say 100 different solutions. All are of same number of bits. So next we will select among them. So out of 100 I will select 30 into the mating pool. So we can apply Rowlett wheel selection or any other selection algorithm. We will put some solutions in the mating pool, say 30 solutions. Then we will do crossover among the solutions in the mating pool. So new solutions will be generated. Next we will replace those solutions in the original population. So original population has size 100, mating pool has size 30. We have selected 30 from the original population put into the mating pool. So those 30 will get replaced with the new 30 solutions. After that, inside the mating pool, what happens? After selection, we perform crossover and mutation. We get new solutions. And this we replace into the original population. So we get initial population was there. After replacing, we get the second generation. Again, we apply the same technique. We again apply Rowlett wheel selection, select 30 solutions in the mating pool, perform crossover mutation, go back and replace the original population. So what happens when we apply Rowlett wheel selection? Usually the better solutions get selected. Few bad can also come. But this technique ensures that the good solutions do not get lost from the population, which is one of the important theories of survival of the fittest. Good solutions come to mating pool, and after reproduction, either it gets transformed to a good solution, or that solution as it is can stay in the mating pool. So this replaces the original population. Okay, and this happens for several iterations, and we stop the process when, say, the overall average fitness becomes more or less constant. That does not change over iteration. So this usually happen like at the final stages of genetic algorithm, when the average fitness does not change. That means the solutions get clustered around the local optima. So doing crossover mutation will change the solution, but will change very less. So the overall average fitness remains almost same. So linear regression. Second, another problem we can discuss is say k-means clustering. I think you heard about clustering techniques, k-means clustering algorithm. So what it means is basically we have a set of points, and we want to make two groups out of the 2 groups or 3 groups. So k groups basically. If k is 2, we want to make 2 groups out of this set of points. So visually we can see this is one group, this is one group. If the data dimension is very high, number of points is very high, visualizing this becomes difficult. At that time, genetic algorithm can be used to find out these groups. So when we do this type of problem, any problem, when we solve using genetic algorithm, I said the first question that I should ask is, what is the final solution I want to get? Here I want to get these clusters. In linear regression, I wanted to get the equation of straight line. So M and C were encoded as chromosomes. In this case, I will encode the cluster center as a chromosome. So if we have two clusters, we will encode as chromosome the cluster centers. Okay. So this is cluster center 1, cluster center 2. Similarly, in this way, we will generate several solutions. This is my initial population. Let's say 1,000 solutions. So cluster 1 and cluster 2. Then, these are basically points in this space. So from now, we can apply the same theory to find the fitness of each chromosome. Like, what is the distance of each point from the closest cluster center? And if we sum up all these distances, we get some value, right? So this distance has to be minimized in k-means clustering. So in this case, we can find 1 by that distance, that is the fitness function, because fitness function is a maximization function. If we get all these distances, distance of each point from the nearest cluster center. So 1 by d will be the fitness value for each chromosome. You can come up with another fitness function also. This is one of the options I am talking about. So similarly, for the next chromosome, we can compute 1 by d, some value. Likewise, we will get a fitness value associated with each chromosome. From there, I can do Rowlett-Wheel selection, then crossover mutation, and the same process can be repeated. So this is how genetic algorithm works. Any questions till now? Any questions?
Am I audible?
Yes, yes.
Sir, as we have, nowadays machine learning algorithms, and they are very highly efficient to fetch the information from the data. So how do you look at about soft computing techniques, and these are going to be still relevant in this changing scenario of the research and all?
Soft computing, soft computing involves all these things: genetic algorithm, fuzzy logic.
Genetic algorithm, maybe particle swarm optimization. Many algorithms are there.
So what is your question? Like, how relevant are these in modern days?
Like I'm saying that nowadays people are using machine learning algorithms related to, let's say, classical machine learning model, deep learning, clustering, and many things are there. And hardly we find very less number of papers based on soft computing. As I can observe, it is my observation.
No, there are dedicated journals for soft computing. So you will get
journals are there, but nowadays publication, research is shifted towards this artificial intelligence side, machine learning part, towards machine learning. So I'm just thinking about how much it is going to be relevant in future. Learning soft computing.
See, the problems, machine learning is definitely very large area.
Yeah.
And like the type of problems we solve using neural networks that I discussed
Yes.
is different from what we are doing using genetic algorithm. So, these two are solving different types of problems. If you see that, so what happens is in neural networks, what we were doing, we have some data which consists of feature vectors f1, f2, and the corresponding labels L1, L2, whatever. So we want to find a mapping from this set of features to the set of labels. Or, I mean, it can be labels means classification levels or regression problems. So some mapping function we are trying to find out through neural network. In genetic algorithm, what we are doing, I mean, we have some functions. This mapping function we are finding here. Na? In genetic algorithm, we know some function. Okay, the function is known. And we want to optimize that function. So for which value or for which set of parameters the function gets maximized or minimized, whatever. Okay.
So that things I know. Actually, you are talking about optimization, right? In machine learning, we are not thinking about optimization and all. But in soft computing, there will be an objective function, and we look at the solution with respect to. Yeah, please.
So, I mean, since we are solving two different problems using the two different techniques, so definitely after genetic algorithm, we have particle swarm optimization, differential evolution, etc. So these are more improved versions of genetic algorithm. So these will never get obsolete because these are like not at all related to what neural networks are doing. These are solving different types of problems. And in many papers till today, you will see that this neural network optimization, or optimization means how the weights get updated. We discussed about backpropagation algorithm, etc. Or choosing the optimal hyperparameters. One question also came regarding that. So all these things can be done with genetic algorithm or PSO. Like what are the optimal hyperparameters to train a neural network, or what are the optimal weights of the neural network that we can estimate using these algorithms.
So maybe soft computing, as you are saying, that soft computing can be used to optimize the neural network based algorithms, neural network based models.
Soft computing can be used is not the correct term because neural network itself is part of soft computing. So the soft computing has different areas. What is not hard is soft, right? So hard computing means we are going for some brute force approach, and soft computing techniques means we are intelligently trying to solve a problem to get near optimal solution. We will not get the exact solution, we may not get, but we are trying to apply some either heuristics or certain greedy search techniques or whatever to get close to the optimal solution, but near optimal. It may not be the actual optimal solution. So these three things are very much used in conjunction also in modern day research. Like fuzzy logic can be used with neural network, genetic algorithms can be used with neural network. So these are combined also in if you see research papers in nowadays, so none of them are getting obsolete, rather they are still very much in the run.
Okay, sir. Thank you, sir. Thank you very much.
So in many cases, as I said, one very difficult problem while training neural network is finding the optimal hyperparameters. We talked about fixing several configurations, learning rate, number of hidden layers, number of neurons, and for that what validation accuracy we are getting. So if we do it for certain number of let's say configuration 1 configuration 1 we get this validation accuracy, configuration 2 we get validation. So we can have this data. So for different 100 different configurations, so among these we choose the one which is giving the best validation accuracy to train the neural network. However, like that may not be the actual best. We may have missed some configuration which can be even better. So we can try to use genetic algorithm to find a relation between C1 and V1 here, or we can try to come up with a new configuration using genetic algorithm which will have a better cross validation accuracy. So all these things can be done using genetic algorithm to make the neural network learn even better.
Yes, sir, you are right.
Hello.
Yes.
Sir, I have one question related to this discussion. Sir, in training the modern neural network or deep learning network, we are still, while training the model, we are still using gradient descent method only. But we can, I have hardly see means any paper that they are optimizing these neural network parameter through this genetic algorithm or evolutionary algorithm like this. They are still using the gradient descent method only that are based on the differentiation. So how these evolutionary algorithm are powerful means why they are not used in the training?
See, the stochastic gradient descent. So I mean, as per my experience, training the model, training the network, you can, we apply this gradient descent. Yes, that is right. But this point that I talked about is not about, weight updates. Rather, the optimal configuration, say eta, number of hidden layers, number of neurons in each layer.
Yes,
So which configuration can give a better cross-validation accuracy. So after getting the error, how we are backpropagating the weights, that is not discussed here basically. So which configuration of this can give a better validation accuracy, that is what we can try to estimate using genetic algorithm.
okay, sir. Thank you, sir.
Yes.
So please do share the PPT, sir, please.
I will share it.
Like yesterday. Yes, sir.
I will share. But today I may not be possible. I will share tomorrow.
Yes, sir. So one more thing, sir. Sir, is it possible to share the recording video, sir? Actually, today's session, I wanted the recording video for today's session only, sir.
Recording, I don't know if TLC is doing the recording. I'm not sure. I don't think is recording done for this one.
Sir, actually, there are network issues in my area.
Okay. I don't think recording is available here.
Okay, sir. Okay, sir. Thank you, sir.
Okay. So I think we have discussed the important part of genetic algorithm. If you have any queries, you can reach out to me via email. So I am writing my email ID here. Okay. Yes. I am just thinking about whether genetic algorithm can be used to do the back propagation. That is what I'm thinking currently. So if I get any answer, I will definitely get back to you. Do you have any further questions? Actually, 4-hour continuous session, I am also getting very tired. So
Yes, sir. Yes, sir. Sir, can you please provide some assignment like notes that I wanted to know, sir, like today's previous session, like how to choose a particular model in machine learning for for like a research purpose or like any assignment purpose for assessment of myself in on career guidance, like so.
Chatu, you need some coding assignment you are asking, right?
Yes, sir. Yes, sir. Yes, sir. Like in connection with model creation, on what basis we can create the models and like assignment on coding. Yes, sir. Yes, sir.
So this we talked now that UCI machine learning repository. Here you can download some data set.
Yes, sir.
UCI machine learning repository. So here you will
UCI.
machine learning repository in Google.
Okay, sir.
Here you will get lot of data iris, then cancer, wine data set. Many data sets are there. So you can download one or two of them and try to train a model. And by defining the model, you apply this grid search and cross validation.
Yes.
First, you divide
Sir,
the data into training and validation set, and then
yes, sir.
the cross validation accuracy to fine tune the model.
So it is ICU data repository, no, sir?
UCI.
UCI data repository. Okay, sir.
Just search here UCI. You will get it. MM repository. This one, huh?
Yes, sir.
So you will get several data sets here. IDs is very
Yes.
popular. Heart disease, many data sets. Any further questions? Achha. So if there are no questions, any questions? So if there are no questions, I can close the meeting. You can reach out to me via email. Okay.
Yes, sir. Yes, sir. Thank you, sir.
Okay, thank you.
I will try to contact you via email, sir. Thank you, sir.
Okay, okay.
Thank you, sir. Thank you very much for the session.
Thank you. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Sir, I can leave the meeting.